On the topic haloalkanes with chapter 7. Okay, so we proceed. Next slide. Okay, so the learning outcome for today is in this chapter we have two subtopic 7.1 and 7.2. The 7.1 subtopic is introduction to haloalkane, and it is about the how to draw. I will teach you how to draw the structures, okay, of haloalkane and classify this haloalkane into a primary, secondary, tertiary, and alkyl halide. Okay, and what is alkyl halide and what is cyclic alkene, cyclic halide, sorry. So second, we will name the haloalkane using IUPAC nomenclature, and then I will teach you how to describe this haloalkane as a compound that contain polar bond and the carbon bearing the halogen is susceptible to nucleophilic attacks. Okay, so we have three minor subtopic in 7.1. Okay, so haloalkane, or we can also call as alkyl halide. So what is haloalkane actually? Haloalkane is a compound, right? Haloalkane is a compound that contain halogen atom bonded to a sp3 hybridized carbon. Alright. So what is sp3 hybridized carbon actually means by? sp3 hybridized meaning that this carbon bonded with this carbon have 4 single bond. Okay, when this carbon have 4 single bond, this carbon are known as sp3 hybridized. sp3 hybridized carbon. So when this carbon sp3 hybridized directly bonded with any halogens. Okay, for the symbol is X. X can be fluorine, X can be chlorine, X can be bromine, X can be iodine. Okay, and these all 4 atoms are located in group 17 of periodic table. Alright, so these halogens are as their functional group. Alright, so usually general formula of haloalkane we use Rx. R for any alkyl group, maybe CH3, maybe benzene, alright, any alkyl group, and X is your halogen. Okay, so general formula we have two general formula for alkyl halide or haloalkane, which is CnH2n plus 1X for a cyclic, or we call as aliphatic haloalkane, and CnH2n minus 1 for a cyclic haloalkane. For example, okay, we have cyclopropane with Cl. Example. So this is cyclic molecule. Sorry. Okay. This is cyclic molecule. So the molecular formula for this cyclic haloalkane, because these have 2 hydrogen, another each of these cyclic have 2 hydrogen, to make sure all the carbon have 4 bonded, and at this side we have 1 hydrogen. So total we have C3, we have 3 carbon, and how many hydrogen here? 5 and 1 Cl. So suit for this general formula CnH2n minus 1 X. Okay, for a cyclic haloalkane, generally I take this example. Okay, we have chlorine, H. Alright, so we have a cyclic compound here is chloroethane. Okay, chloroethane with the formula C2. Okay, H5, C2H5, Cl. Alright, so this is CnH2n plus 1x. But this one is CnH2n minus 1x. So this is the difference between a cyclic haloalkane and a cyclic haloalkane and acyclic. Okay, acyclic meaning that very normal haloalkane. Right. So classification of haloalkane. Okay. Haloalkane are classified according to the halogen nature of carbon atom bonded to the halogen. Okay. Tak nampak sekerat. Okay. So general formula of this compound. Alright. So general formula of this compound classification. Okay, when we have CH3Cl, so the general formula is methyl halide because this halogen bonded with CH3 metal. Alright, it is no primary, secondary or tertiary because this halogen when directly bonded with CH3, it being classed in methyl halide. Alright. For primary halide, when this halogen, either chlorine, bromine, fluorine or iodine, directly bonded to the primary carbon. Okay, directly bonded to the primary carbon. Okay, directly bonded to the primary carbon. So usually I call this as alpha carbon. Usually I call this as a alpha carbon. What is alpha carbon? Alpha carbon that hold the functional group. Alright. So when this halogen directly bonded to alpha carbon and this alpha carbon is primary, have primary class. So automatically this class of haloalkane also being primary halide. Alright. So this is important to you, okay, students, to look at to class the alpha carbon. Okay. To know the class of alpha carbon, you have to calculate, you have to count how many neighboring carbon that bonded to this alpha carbon. Okay. And the second example here, we have secondary halide, secondary haloalkane. So now we're focusing on this alpha carbon, and our alpha carbon is this carbon. Why? Because this carbon hold this functional group, and this alpha carbon bonded with another two carbon. Okay, that's why this alpha carbon is secondary. So automatically this haloalkane turn to be secondary class. Okay, secondary halide. Okay. So general formula for tertiary halide is when your alpha carbon is tertiary, we have 1, 2, 3 neighboring carbon for the alpha, so automatically halide is tertiary halide. Sorry. Okay, now let's move on to the halogen that directly bonded to the benzene ring. What happened to the class actually? Alright, so that halogen that directly bond with benzene, we are no longer classified in primary, methyl or tertiary or secondary. We class it as a aryl halide. So what is aryl halide? Aryl halide is halogen that is bonded directly to the benzene ring. Alright, that is aryl halide. Compared to the next compound here, this halogen not directly bonded to benzene but is bonded to this carbon. This is your alpha carbon. Okay, and this alpha carbon is not in the benzene ring, so it just classify as the normal before. Okay, as I teach you earlier. So this alpha carbon is primary, has a primary class. Okay, primary class. So the alpha is primary, so automatically it is not aryl halide because this is not carbon benzene, and also we can classify it as a primary halide. Okay, next is halogen that directly bonded with alpha carbon in a cyclic compound, and this alpha carbon is secondary. Why? Because one carbon, two carbon, neighboring two carbon, so this alpha is secondary carbon. Automatically your halide turn to be secondary halide because bonded to secondary carbon. Okay, for example, we have some more example here. We have primary class of halide. Why? Because this is our alpha and only one neighboring carbon. This is our alpha. Okay, we have two neighboring carbons, so secondary class. This is our alpha, and we have three neighboring carbons. CH3 we got 3, so tertiary class. This is our alpha carbon, and this alpha carbon have 3 neighboring carbons, so tertiary class. Alright, for methyl, when your halogen directly bonded with the CH3 group. Okay, now without further ado, we proceed with how to give a name to this haloalkane compound. Okay, same goes with the alkane group that you have learned before. Okay, in previous lecture. Haloalkane are named as alkane with halogens. Okay, are named as alkane with halogen as a substituent. Alright, so the first and foremost important things you have to know is you have to numbering the parent chain. Okay, you have to numbering the parent chain so that your substituent which is your halogens encountered the lowest possible number, right? So when you got 2 or more halogen, we can use prefix like di, tri, tetra. And when you have fluorine, we call as fluoro as a substituent. When you have chlorine, chloro. When you have bromine, we call as bromo. When you have iodine, we call as iodo. Okay, and list them in alphabetical order along with the number of substituent. Alright, for example, okay, we have how many carbon here, class? Right, so now the longest carbon chain, okay, the longest carbon chain is 4, right? The 4 longest carbon chain, and we have substituent here, which is bromo. Right, we have 4 carbon as parent, which is butane. Alright, so now we have to numbering where the bromo is located, or where is bromo is numbered in the parent chain. So we have 2 ways. Either we number from left to right or right to left, right? If I choose to numbering from here 1, 2, 3, 4, okay, so my bromo got number 3. If I choose from left to right, okay, the red font, 1, 2, 3, 4, 4, sorry. So my bromo got number 2. So I choose the red one, 2 bromo, because the lowest possible number for my bromo, 2 bromo butane. Alright. For example, here we got 6 carbon. Okay, we have 6 carbon, and we have more than 2 substituent. We have bromo, we have chloro, and also we have methyl as our substituent. Okay, So here chloro, okay, so here is bromo, and we have methyl. Okay, now we have to numbering. We know the longest carbon is hexane. Okay, but the problem is to numbering, alright, to give numbering. So make sure when you number all the substituents, when we total up this number, got the lowest possible number. So here bromo 1, chloro 3, methyl 4. 1 plus 3 plus 4 is 8. Am I right? 1 plus 3 plus 4, the location of substituent is 8. If I numbering from right to left, okay, the summation of number will be bigger. So we choose this way to numbering. So how? Between bromo, chloro and methyl, B come first, alphabetical order. So 1 bromo. Between chloro and methyl, we call chloro first. So 3 chloro. And methyl will be the last substituent that we call out, which is 4 methyl. Right? Okay, clear? Okay. So another example is we have heptane, 7 carbon, and here we have a little bit a complex substituent. Okay, this substituent is 2-fluoroethyl, because this is carbon number 1 directly bonded to the parent. So fluoro is at carbon number 2. This is 2-fluoroethyl. We put a bracket here to show this is substituent. 2-fluoroethyl as a substituent at carbon number 4 parent chain. So 4-2-fluoroethyl heptane. So next example is we have a cyclic. We have cyclic halide, which we have 3 substituent, chloro, and we have 2 methyl. Okay, make sure you numbering so that the total of substituent get the lowest possible number. So methyl number 1, methyl number 1, chloro number 2. So the total number will be 4. Alright. So in alphabetical order, we call chloro first. So 2 chloro because C is come first. Then 1, 1 because we have 2 locations. We have a location of methyl at the same carbon. So 1, 1. Okay, number kita koma and dash dimethyl to show the number of methyl here is 2, dimethyl cyclopentane. Okay, what happen if we have cyclic with a double bond? Okay, when we have cyclic in double bond, confirm we must to numbering 1 and 2 at this carbon-carbon double bond. But here I choose to number 1, 2, 3 and 4 so that my bromo got number 4. Okay, but okay, if I choose the other way, example 1, 2, 3, 4, 5, my bromo get number 5. It is not correct. Okay, for IUPAC, rule nomenclature, we must numbering so that our substituent get the lowest possible number. That's why we call 4-bromo cyclohexene. Why hexene? Because the ring have 6 each. Okay, bucu 6 cyclo, and hexene because this is carbon double bond, and not hexane but hexene. Okay, so this is example of benzyl methyl and so on lah, right? So this is benzyl, okay, and this is chloride, or we can name as, the other way to name is, give this as a substituent. This is chloromethyl and this is benzene, so we call chloromethyl benzene in bracket because this is substituent. Alright, so here we have aromatic compound. So the general formula that you have learned previous lecture, benzene with CH3 we call as toluene. So this is carbon number 1. Automatically chloro will get number 2. So we can give a name to chlorotoluene. Or orthochlorotoluene. Ortho. You can replace the number 2 with O for ortho. Orthochlorotoluene. Alright. So the structure of haloalkane. Okay. So actually the carbon and halogen is polar bond. Okay. Is a polar because the halogen is electronegative. Because this halogen located in group 17, that's why it's very electronegative, and it pull out all the electron here, so meaning that at this side have rich region of electron. Okay, so at the carbon that bond with halogen is poor region of electron, so this is electrophilic site. This carbon is electrophilic site. Alright, so this carbon bearing the halogen is susceptible, meaning that it exposed. Okay, it's exposed with the nucleophilic attack because this carbon is very low density of electron, poor region of electron. So it best part, it is best location, best spot for the nucleophilic. The new nucleophilic to attacks. Alright. So haloalkane are reactive, undergo two type of reactions. One is nucleophilic substitution, and the other one is elimination. Alright. So in these nucleophilic substitutions, actually there is two way. One is Sn1, one is Sn2 that I will tell you, that I will teach you later. So please stay tuned. Alright. So the importance of haloalkane, okay, we still in chapter 7.1. The importance of haloalkane, it is best used for aerosol, propellant, refrigerants, and solvent for decreasing. Okay, so chlorofluoroalkane, meaning that we have chlorine, we have fluorine in our alkane. So this is for our aerosol, fumacula, Rixac, and so on. Okay. So tetrachloromethane meaning that we have carbon with tetra, meaning that we have 4 chlorine. Okay, this is tetrachloromethane. Is a best compound, okay, for use in fire extinguisher. Okay, DDT is also a haloalkane. We conceive of halogens is used to destroy mosquito with insecticide lah, with spread malaria. Okay. However, the use of haloalkane will be effect to our ozone layer because this will deplete. This will make our ozone layer become thinner. Alright. So 7.2. Chemical properties of haloalkane. Okay. If you don't see this lecture very well, I suggest to you to look at or to see the lecture note in your books or in your teams, group teams. Okay. 7.2 chemical properties of haloalkane. So I will explain to you about 30 minutes about 7.2 subtopic. After this 7.2, we have a short quiz. Alright? Explain the nucleophilic substitution reaction of haloalkane. Alright? So these nucleophilic substitutions, okay, because halogen, we have halogen, so this halogen will be substituted with a new nucleophile. Right? So we have two method or two way of nucleophilic substitutions. The first one we call Sn1 and the second way is Sn2 mechanism. Mechanism is the way. Okay. So How Sn1 and Sn2 mechanism of a given haloalkane. This you will learn details more in your tutorial class, but I will teach you a little bit for the surface what is Sn1 and Sn2 is about roughly. Alright. Then I will teach you compare the reactivity primary, secondary, tertiary haloalkane towards hydrolysis and alcoholysis. But this again you will learn detail in your tutorial class. Okay, so I will explain to you the elimination, elimination reaction of haloalkane, and explain the use of haloalkane in synthesis of Grignard. Okay, you never heard about this Grignard reagent. This Grignard reagent is multi-purpose reagent. When you have this Grignard reagent, it can be used to form many of type of compound, organic compounds. So Grignard reagents, the main source of Grignard reagent, the main reactant of Grignard reagent is haloalkane. So from haloalkane, we will form Grignard, and this Grignard as intermediate reactant to form many more of reactants or organic compound. Okay. So how to use Grignard to react with another compound, this you will learn in your tutorial. I just teach you in this lecture on how to form Grignard compound. Alright. So nucleophilic substitutions. Okay. Haloalkane undergo nucleophilic substitutions reaction in which the halogen atom replace. The word here is replace. Okay. The word here is replace. What is replace? Replace is substitute. Alright. In this reaction, the nucleophilic attack partially positive of this carbon bearing, this carbon alpha. Okay, this carbon bearing the halogen, or we call as carbon alpha, attacking this carbon bonded to the halogen. So why? Because why the carbon is being attacking? Because this carbon is susceptible to being attacked, because this is special carbon deficient species of electron. Okay, here the general formula, we have alkane with bonded with the halogen. Okay, this is halogen. So all the electron here are push out, okay, are pulled by this halogen, because halogen is very electronegative. So this carbon that hold this halogen become partially positive, deficient species of electron. So the new nucleophile waiting for this moment. Alright, so this nucleophile, the new nucleophile will attack the carbon alpha so that it will replace the position of halogen. Alright, see how this trick. Okay, the new nucleophile will replace the halogen, and this halogen will break. Okay, it actually a sadist penceritaan yang sadis lah, macam ada perebutan kuasa lah, lebih kurang. So hydrolysis of haloalkane with aqueous solution of sodium hydroxide. Right. So alkaline hydrolysis is carried out by boiling haloalkane. This is a process. We must boil the haloalkane with a sodium hydroxide to form an alcohol. So what happened actually? This sodium hydroxide, okay, also bring a nucleophile here. This sodium hydroxide got OH minus, and also sodium will become an A plus. Okay, so it bring both nucleophile and electrophile. Okay, so here OH minus from sodium hydroxide will replace with halogen. So now before we have haloalkane, halide, and after we react with new nucleophile, will become a new product with alcohol. Okay, so from halide turn to be alcohol. Why? Because it undergo the nucleophilic substitution, and it will also form a byproduct. Okay, byproduct hasil sampingan with NaX. In this case, kalaulah your halogen is Cl, so it will form NaCl. Alright. For example, here we have we have 2 methyl propane react with sodium hydroxide. So this sodium OH minus will substitute, tukar tempat okay, substitute nucleophile. That's why nucleophilic substitution. Okay, so it become alcohol. Okay, so this is example how the haloalkane undergo nucleophilic substitution by OH minus. Okay, sodium hydroxide. Okay, another example is we want to replace Cn minus, the new nucleophile also, which with strong nucleophile. So this Cn minus will replace with halogen, and this halogen is being removed and will break from the alpha carbon. And what happened? We will form a new product with cyanide form, and this halogen will be eliminated. Alright. So example here we have 1 bromoethane. Okay, here this is alpha carbon that hold this bromine. So Cn minus will substitute with the bromine, and bromine will be eliminated from the haloalkane itself. Okay, so now we have a new product with cyanide, new nucleophile, and the byproduct will be KBr. This will form a new product. What new tu byproduct, hasil sampingan, hasil buangan KBr. Okay, selain daripada instead of alcohol, instead of cyanide, we can form amine. Okay, haloalkane can form amine. How? Okay, by react with ammonia. Alright. For when react with ammonia, so what happen? It will become NH3 plus X minus. The first thing, the first molecule ammonia came in. So after that, after the reaction is proceeds, so this ammonia also consists NH2 minus and also H plus. So NH2 minus will replace with NH3 plus X minus, nucleophilic substitutions that become amine compound. And so as a byproduct, it will form a salt here, garam, garam ammonium chloride, for example. Okay, so we have chlorine, chloroethane. If we use an excess here meaning that we have plenty or more reaction with ammonia, so tak payah buat 2 step, just buat excess ammonia, just write down excess. So what happen? You terus pergi ke end product with a ethan amine. Right, ethan amine, and you will form a salt here. There is no errors. Okay, tidak ada kesalahan jika you tak tulis byproduct. The organic kita focus on the main product, and our main product is amine. Alright. Okay. The fourth reaction again. Haloalkane can also be react with simple by water. Water bring OH minus and also H plus. So OH minus nucleophile will substitute with your halogen, okay, and this HX will combine to form a byproduct of HX. Alright. For example, we have chloroethane react with water, and we form a new product, ethanol. Chloroethane to form ethanol, and HX supposed to be is HCl because we use Cl. Alright. So reaction of haloalkane with alkoxide. When RX react with alkoxide, what is alkoxide actually? Alkoxide is RO minus. Alkoxide usually it came from ether. Okay, as you know, ether, for example, CH3O, CH3, we have alkoxy group. So this alkoxide brings CH3O minus and also CH3 plus. Okay, so this is what we call alkoxide. Okay, so this alkoxide ion from ether will substitute with the nucleophile, which is halogen. Okay, nucleophilic substitution, and will form a new ether with a longer ether. Okay, for example, we have bromine for our halogen, and we have methoxide ion. So this methoxide ion will replace halogen and become a new new ether with a longer carbon chain. Alright, next, we have RX alcohol with halogen atom substitute with RO produce HX. Okay, so this is example. Previously we call alkoxide. Here we also have alkoxide, but this come from alcohol. Previous come from alkoxy. Right? So this is alkoxide come from alcohol. So alkoxide that come from alcohol, RO minus, and we have H plus. When this nucleophile from alcohol replaced with the halogen from haloalkane, okay, substitute, so we form again alkoxy with a longer carbon chain, and the byproduct here is HX. For example, we have methanol react with 2-bromo 2-methylpropane, and we will form a new alkoxy with a byproduct of HBr. H come from alcohol, Br come from haloalkane. Okay, the difference here is the between E and F, okay, is the byproduct. Alright, so 7.2 mechanism of Sn1 and Sn2. Okay, saya dah cerita tentang nucleophilic substitution. Now I want to detail to you about the way how the nucleophilic substitution is proceed, or it has been processed. Right? So there is two important mechanism for the substitution reaction. One is unimolecular. Uni meaning one. We have one Sn1, S meaning that nucleophilic, N S is substitution, N is nucleophilic, one is unimolecular. S is substitution, N is nucleophilic, 2 is bimolecular, meaning that 2. Alright. Sn1. Okay, we look up at Sn1. The term unimolecular means there is only one molecule involved in the transition state of the rate limiting step. Alright. For Sn1 reaction is governed mainly by the relative stabilities of carbocation. Okay, so Sn1 preferable. What meaning here is Sn1 is preferable for tertiary haloalkane. Okay, so when we involve tertiary haloalkane undergoing nucleophilic substitution, it choose Sn1 way. Okay, why? I will tell you in a short time. Relative reactivity of haloalkane in Sn1. So Sn1 prefer tertiary, and then secondary, primary, and it definitely not choose a methyl haloalkane. Okay, so this is reactivity undergo Sn1 reaction. So if you have tertiary haloalkane, it undergo Sn1 mechanism. So the rate of Sn1 reaction does not depend on the concentration the new nucleophile. Okay, does not depend on the concentration of the new nucleophile. It only depend on the concentration of our haloalkane. Alright, if you have alcohol as your new nucleophile, it will not defect. Okay, it will not affect in your rate of reactions. Okay, because Sn1 only depend on the concentration haloalkane. This is first order. That's why one is actually first order reactions. It depend only on the haloalkane itself. Example, we have tertiary haloalkane. Of course, it's favorable to undergo Sn1 reaction mechanism. So we have new nucleophile here with H2O, that's bring OH minus, our new nucleophile, and this concentration of new nucleophile is not affected at all for rate of reactions. Okay, so I just take a very roughly idea about what is Sn1 actually about. Okay, so what happened actually in Sn1, the haloalkane, okay, the carbon bearing halogen here is polar bond, it start to break. Okay, it start to break slowly. You have to put slow. Okay, and you have to write rate determining step. And when it break, it become carbocation. What kind of carbocation? It form a tertiary carbocation. Okay, the first step for Sn1 is to form carbocation. Okay, and of course Br minus as the halogen that being break. The next is we have water. Water bring nucleophile, and this nucleophile will attack this carbocation because this carbocation is susceptible to being attacked. Okay, poor deficient species of electron. When it attack, it put a bond here. It will form a bond here, but it is not stable because it's ion. So what happened again? Water will take hydrogens and it will form a new alcohol. Okay, alright. So the roughly idea is for Sn1, the first step is forming carbocation, and the second step is nucleophile attacking carbocation. So 2 steps minimum. Alright. So detail you will learn in your tutorial. Okay. For Sn2, we have bimolecular nucleophilic substitution, which is Sn2. 2 what? 2 is bimolecular. 2 molecule. Mean that transition state rate, the limiting step involve the collision of 2 molecule. Alright? So Sn2 reaction are governed mainly by steric factor or steric effect or steric hindrance, whatever. That bulky alkyl group blocking this carbon, blocking this alpha carbon. Alright? So steric effect, what is steric effect? Steric effect is a relative rate caused by the space filling properties of those part of a molecule attached at a near reacting site. Alright? So in Sn1, I don't mention about steric effect. Okay, I just mention about carbocation, the stability of carbocation. But in Sn2, I mention about the steric effect. Okay, so Sn2 reaction depend on the size atom. Okay, Sn2 reaction depend on the size atom or group that attach to the alpha carbon. What is alpha? Alpha carbon is carbon that bearing with the halogen. Alright. So the presence of bulky alkyl group, will blocking the nucleophilic attack, the new nucleophile to attack the reaction. So meaning that if you got more alkyl group surrounded this alkyl, it make the Sn2 is slower. That's why Sn2 don't like tertiary haloalkane, because tertiary haloalkane have many alkyl group blocking the alpha carbon. So the reactivity of Sn2 actually is depend on the less alkyl that block the alpha carbon or steric effect. So methyl haloalkane is the fastest, okay, is favorable to undergo Sn2, and the primary is second one lah, right? Okay, the rate of reaction depend on the concentration of haloalkane and concentration of the new nucleophile. See what I mean? So in rate reactions for Sn2, haloalkane and new nucleophile both are involved to determine the rate of reactions. Okay, both reactants are involved in determining rate of reactions. So this is second order, 1 plus 1. Order is second. So the mechanism of Sn2 actually very simple, one step. Compared to the Sn1, 2 step. Alright. So the Sn2, the first thing is you have to draw tetrahedrally the haloalkane. Alright. So here example, I want to draw chloromethane. Okay, chloromethane because favorable to undergo Sn2. Chloromethane actually CHCl. This is chloromethane. You draw in tetrahedrally. So how to draw tetrahedrally? So make sure the halogen that want to be kicked out from your haloalkane, we must put here Cl kat sini. Kita kena letak Cl kat ujung. So this is carbon alpha that bearing with the halogens, and this is another atom that bonded with the your what? Alpha carbon. Right? So what happen after you draw in tetrahedrally for mechanism? So you want to backside attack, or we call as backstepper. Backstepper ni tahu tak? Tikam belakang. Ada ke kawan tikam belakang ni? Okay, so backstepper for Sn2. So what happen is this new haloalkane will attack this alpha carbon backstep. Okay, this new nucleophile, maybe OH minus, we just put OH minus here. Okay, we just put OH minus here, attack this carbon, and this will be halogen will be slowly being removed, and we call it as transition state. The new nucleophile, okay, in form to form a bond, in a process to form a bond, and this halogen in a process to break the bond. Okay, this called transition state. Very slow to form this transition state. After this transition state, if it's not stable, very fast reactions. So this halogen will be kicked out from the haloalkane. Remove here. Okay, kick out, and we will form a new compound. Okay, very simple. Kalau you nampak dia macam payung, payung asalnya payung dia macam ni, akhirnya payungnya macam tarik ke belakang, because OH dah masuk kat sini. Alright, so in Sn2 reaction, the nucleophilic attack from the back side. Remember, backstepper Sn2. Okay, one step reactions. Steric effect is important for Sn2. Okay, methyl halide is very important. Dia tak suka yang banyak cover sangat alpha carbon, sebab dia nak backstep. Payahlah kalau banyak bodyguard. Okay, so electrophilic carbon that is from the side directly opposite bonded to the halogen. Maksudnya the new nucleophile will substitute your halogen in opposite way. Kalau tadi halogen duduk belah kanan, so dia backstep, dia akan masuk belah kiri. Kalau halogen duduk depan, macam itulah dia akan opposite side. Okay, so the transition state involve partially bonding. Okay, transition state tadi kita mention, dia akan membentuk partially, sekerat kerja, maksudnya in the process of forming a bond and in the process to break the bond. Alright, so backside attack cause a product form as inverse configuration. Okay, inverse configuration, payung terbalik tadi. Kalau tetrahedral tadi macam mana, so dia akan backstep ikut opposite. The new nucleophile will take place in opposite direction of your halogens. Okay, so dia macam di sini turn the tetrahedrons of a carbon alpha inside out like umbrella caught by the wind. Macam apa? Macam ada payung tu kan, payung tertarik tu kan. Macam itulah. Alright, competition between Sn1 and Sn2. What are the differences and what are the similarities between Sn1 and Sn2? Note that secondary haloalkane can undergo both. Alright, remember, saya just mention tentang tertiary dan primary. Saya tak mention tentang secondary. So secondary ni macam mana? Dia nak masuk mana? Dia nak kawan dengan, dia nak undergo nucleophilic substitution ikut Sn1, ataupun dia nak undergo nucleophilic substitution ikut method atau ikut cara Sn2. Sebab dia tengah-tengah. Okay. So here, kalau secondary haloalkane, okay, kalau secondary haloalkane, macam mana kita nak determine dia nak undergo Sn1 ke Sn2? Kita tengok nucleophilic yang nak replace tu. Ada new nucleophilic. Kalau lah nucleophilic yang nak replace tu lemah. Saya ulang Kalau lah nucleophilic yang nak replace tu lemah, example water, ammonia, alcohol, ini example of weak nucleophile. Bila kita involve nucleophile yang lemah ni, so dia akan favorable to Sn1 method or Sn1 mechanism, nucleophilic. Tapi bila secondary haloalkane ni, dia react dengan strong nucleophile. Okay, strong nucleophile, for example OH minus, cyanide, sodium hydroxide, alkoxide. Secondary haloalkane ni akan undergo nucleophilic substitution ikut Sn2 method. Alright. Tapi kalau dia primary haloalkane, memang tak payah tanya, dia memang undergo Sn2. Cuma secondary saja. Secondary haloalkane you kena tengok nucleophile nak masuk, nak ganti tu kuat ke lemah. Secondary haloalkane sahaja. So example, okay, kita nampak dia kat sini. Determine whether substitution reaction will take place Sn1 ataupun Sn2. Okay, jawapannya dia akan favorable Sn1. Kenapa Sn1? Okay, sebab dia boleh buat rearrangement. This you will learn more detail in your tutorial class. Kenapa? Sedangkan kalau tengok di sini dia secondary kan? Dia secondary kan? So ini pula weak kan? Weak haloalkane. So supposed to be Sn1. Memanglah Sn1 lah. Alright. So ini yang tadi saya bagi tahu, kalau kita ada secondary haloalkane, kalau kita buat strong nucleophile, it undergo Sn2. Kalau weak, dia akan undergo Sn1. Alright. So as to conclude, okay? To conclude, what is Sn1? Nucleophilic substitution. Sn1 adalah two-step mechanism. The first one, you want to form carbocation. The second step, you buat nucleophilic attack the carbocation. Second step. Mungkin lebih, tapi minimum 2 step. Okay, sebab mungkin dia melibatkan rearrangement of carbocation to form more stable carbocation. Okay, if you not understand here, it's okay. Okay, but remember to find out the answers what you don't know in your tutorial class. Okay, for Sn2, it only involve one step of reactions. Kan dia backstepper. Dia backstep the transition step, lepas tu dia akan form a new product. One step sahaja, cuma slow dan fast. Okay, Sn1 dia unimolecular sebab kepekatan haloalkane sahaja menentukan kadar tindak balas. Only the concentration of haloalkane that determine the rate of reactions. For Sn2, haloalkane and also new nucleophile both is involved to determine the rate of reactions. The order of Sn1 1, the order of Sn2 2. Alright. So usually nucleophile Sn1 involve weak nucleophile and strong nucleophile for Sn2. Involved in carbocation rearrangement for Sn1. No carbocation at all for Sn2. Okay. Reactivity, so preferable, okay, preferable tertiary carbocation, okay. The reactivity, okay, preferable methyl. Maksudnya lagi sikit yang block carbon alpha lagi baguslah undergo Sn2. Steric effect is less important. Tak kisah siapa block, dia nak form saja carbocation. Steric effect is important in Sn2. Alright. As a conclusion, kita boleh kata methyl halide dan primary akan undergo apa? Sn2. Sebab methyl halide dan primary dia less steric effect. Okay, tengok saja kelas. Oh, primary methyl halide Sn2. Tapi kalau tertiary Sn1. Cuma bahayanya kalau dia secondary. Bila dia secondary haloalkane, nak undergo mekanism mekanism ni cara detail lah, attacking and so on kan. So for secondary haloalkane, you kena tengok pula dia punya nucleophile tu kuat ke lemah. Alright. Sorry student for the technically mistake lah, kesilapan teknikal minta maaf lah daripada pihak saya So we have another one slide, last slide. Okay, elimination reaction. Okay, so kita dah cerita tentang detail dah. Kita kata haloalkane undergo nucleophilic substitution, yang mana saya dah bagi tahu detail Sn1 dan Sn2. Alright, so now saya nak bagi tahu tentang elimination. Elimination haloalkane, kita akan buang. Elimination maksudnya D ni kita eliminate. Okay, D ni eliminate. Jangan suka-suka hati guna D tau. D kemboja, maksudnya buang kemboja lah. So jangan suka-suka hati guna sedap nama. D for in chemistry, D mean eliminate. Eliminate apa? Eliminate hydrogen. N apa? N halogen. Kita eliminate H and X. Dalam mana? Di dalam haloalkane. Alright, so here we have alpha carbon that whole halogen, and we have beta carbon that whole hydrogen. This adjacent carbon will remove, okay, will eliminate hydrogen and halogen. Okay, I repeat, this adjacent carbon beta and alpha will remove hydrogen and halogen and will form a unsaturated compound which is alkene. Alright, so what product will form after elimination of dehydrohalogenations is alkene. But remember, kita selalunya kita guna bahan juga, bukan boleh buang-buang suka hati. So kita ada bahan that we use. Usually we use strong base, sodium hydroxide, potassium hydroxide in ethanol. Dalam ethanol, so we can use, kita boleh simple tulis ethanol ataupun ETOH, dan tulis bawah ni reflux. Reflux ni dia jenis pemanasan juga. So kalau KOH ethanol reflux, baru boleh you remove dehydrohalogenation and it will form alkene. Okay, for your main product. Okay, so that's all for today. Sorry for inconvenience. I hope yang dengar terima kasih, yang belum dengar lepas ni pastikan awak dengar betul-betul dan jawab soalan yang tertera. Scan QR code, ada 5 soalan semuanya. Kalau betul-betul awak join dengan saya dari awal, awak boleh jawab dengan mudah lah. Okay, so saya doakan yang terbaik. So jumpa lagi kami for next Wednesday. Dari saya, Puan Siti Aminah, Unit Kimia. All the best.